is it tells you that this plane is heading due east, right? Correct? It's heading due east, and what's its airspeed? 480, right? So the plane is going due east, but it's rising, and its speed of kilometers an hour, right? And it's rising at what rate? 80 kilometers an hour, correct? So what I'm saying is in this direction right here, this is its direction going east. Its direction, this is looking at the plane from the side. So if you were looking at it from the side, you would see it going up, traveling to the east.
Yeah, so what are you drawing as speed? Right?
What I'm doing is, this is going up, yeah. So imagine the ground is like right here. So like the surface of the planet, that's a great, let me put that perspective in, that's a great thing. Like here's the surface of the planet. Do you understand what's going on here? And that's east right there. So we want to know how fast is this plane moving due east. The reason we're doing that is that airspeed and ground speed, they're not the same. Airspeed is the speed with respect to the air. Ground speed is the speed with respect to the ground. When you look at like traffic maps of planes, it's a global map, and then you see dots where like the planes are. Is the ground speed, is the height of the plane above the ground relevant for ground speed? Only the overall calculation if no, it's not. Just say no. I'm sorry, what am I saying? So if you're going straight up at 10,000 miles per hour, what's your speed with respect to the ground? 0. But if you're going 10,000 miles an hour to the east, your ground speed is 10,000 miles per hour with respect to the ground. So your change in height doesn't matter. The reason we need to find this due east is this is not your ground speed right there. It's not traveling 480 kilometers per hour due east. What?
That's your flights.
That's the airspeed. That's the airspeed through the air. So how do we do that? What theorem do we use right here to find that missing number? Use the Pythagorean Theorem. So you know that this is 480 squared minus 80 squared, the square root of this, right? And I think it's like 473.3, about that, right? Okay, so that right there gives you how fast the plane is moving due east. The other force that is acting on the plane as it travels through the air is the wind. And the wind is going to the northeast, right? The wind is going to the northeast. So we need to change our perspective. We need to now look down. All we now know, what we just figured out, is this plane is moving due east. How fast? 473.3 kilometers an hour, correct? But the wind speed is going to the what direction? I think it's going to the northeast. Was that it? So let's go from right here to the northeast at 100 kilometers an hour. So if we wanted to know the ground speed, what do we have to add together? We have to find the magnitude of that new resultant vector. So what does this vector represent right here? We're looking down. What does that, so this vector right here, see that triangle right there? Imagine that triangle is sitting right here above the board. It's going up and then down like this, right? But you don't care for ground speed if it's going up or down for that matter, right? We know it's going due east at 473. We know that this vector, the wind is acting on it at 100 kilometers an hour to the northeast.
Well, it's coming from the east, it's going south.
Is it going? No, I think it's blowing to the northeast, right? If the airspeed is to the northeast, it's going to the northeast. It says to the northeast, not from.
15?
No, it's 13. To the north. It's okay. It's okay. Similar thing. But here's the thing. That vector, what does that purple vector represent? That is the what of the, like that is the actual what?
Ground speed.
No, the vector is not the ground speed. The magnitude of that vector is the ground speed. What does that vector represent? The actual path of the plane if you were looking straight above. If you were looking straight above, like from orbit, you would see the plane traveling along this path. The plane would be like, I'm going east, but the wind is pushing it along that purple. So first we need to find, and it's rising, but for ground speed, we don't care, right? So what we need to do right now is I want to know what are the components of that purple vector right there. Well, how many vectors are we adding together? 2. So let's put these vectors in component form. And just to be simplified, this is 2 dimensions. When you're dealing with 2 dimensions, everybody, you can just call side to side I and up and down J. When you're dealing with 2 dimensions, you can just relabel them. That's totally fine. So what is this vector? What is this vector right here in component form? So this is the plane. So that's what the plane is trying to do. What's the component for that? Correct. I, right. Now we need to figure out this one though. What are the components for that one? 100 cosine 45 degrees I plus 100 sine 45 degrees J. What is it's the same thing, right? So what do we have here? 100 times root 2 over 2I plus, 100 root 2 over 2J. So you have 50 root 2I plus 50 root 2J. So the actual path of the plane would be modeled by what vector? What do you have to do with these two vectors? Add them together and you end up with 473.3. Oh, got it. Let me close the parentheses first. Plus what? 50 root 2I plus 50 root 2J. So this right here is the path of the plane, right? That's the path. If you want to know what the actual ground speed is, what do you have to do with that vector? Take the magnitude of that vector. You need the magnitude of that vector to actually get the ground speed. So that's just going to be what? 473.3 plus 50 root 2 squared plus 50 root 2 squared, square rooted. And it comes out to like 586, I think. Anybody have it? I think it's 586. Anybody? The ground speed. So that's the magnitude of the path of the vector. Sure. Does it make sense that it's larger than 480? Why? Why should it be larger than 480? Yeah.
Because it's still the wind's still blowing to the east.
To the east. Yeah, it's still working with the plane to a certain degree. Exactly. It's working with the plane to a certain degree. Exactly. So I'm going to draw for you a couple vectors. I'm going to call the first one, let's say, we'll call this one W right here. And let's call this one V. These two vectors represent any two vectors in 3 space. Any two vectors. Any two vectors. So let's call W, just to give it components, we'll call it something that looks like this. And I'll put in the little hats in a second. Plus W3K. We have like this. And V is any other vector. I'm just labeling it with this convention. W3K, like this. So these are any two vectors in 3 space. Any two vectors in 3 space. You with me so far? Okay. So I'm going to then draw this vector in right here. Can you tell me what that vector, that red vector, is equal to? What is that red vector equal to? Anybody want to tell me? What? No. It's not W plus V. What is it? Who has it? I hear a lot of things out there. One of them is, what is it? It is V minus W, correct. This is V minus W. So you have a triangle. What you have to realize at this point is if you have two vectors in 3 space, connect it with that third vector, we're forming a triangle in 3 space. What does this triangle represent? Well, any triangle in 3 space is a plane. Do you agree with that? It's sitting on a plane. Like, these aren't curved lines. So no matter how this is oriented, however we do it, like we have two vectors like from here to these 2 points and connect the other two, you can always get a flat surface on there. You with me so far? So theoretically, we have a triangle that we can kind of treat like it's in 2 space. Now, a really, really, really useful thing to know is this angle measure. Sometimes you want to find that angle measure between 2 vectors. It's really, really important to find out sometimes, a lot of the time actually. In 2-dimensional space, which is what we're in now, even though these are 3-dimensional vectors, because you can lay a plane across this triangle, you can treat it like it is in 2 dimensions. There are a couple laws that help us find angle measures inside triangles. One of them is the law of sines. We don't really have those other angles though. You need another angle to work with. So if you only have one angle, if you have no angles, but you have 3 side lengths, what's the law that we can apply here? The law of cosines. Can anybody tell me what the law of cosines will be? Let me start you off first though, okay? And I'm very happy that you're happy about this because I really love the law of cosines. I'm going to start with this. If I start you with this as your third side, Cameron, if I start that with the third side, can you tell me what the rest of the law of cosines tells you, Cameron? I know, but just think, it's the other 2 sides, so what are they? But what about them? Yeah, the magnitude of them, right? They're adding them together, I think, right? Is it plus or minus? Minus. It is definitely minus. Good. Yep. theta. Nice, exactly. Very nice. Yay, exciting. For me, if you stripped away everything that was crammed into my head in high school and math classes that I had to work with, like if you stripped away my identity, like what would my core thing be? It would be concave up is happy, concave down is sad, and the law of cosines. Like that would be, like that right there is gonna be like the last thing. I'm gonna forget my name before I forget that. It's just there. C squared A squared B minus 2B cosine C, cosine C. Okay. Each of those things is an operation you know how to do. You know how to do all of those things. So for example, can you subtract W from V? Is that something you could do? Absolutely. So if you subtract the two, let's do that subtraction. If you do V minus W like this, what are you going to end up with? V1 minus W1, I, right? Plus what? V2 minus W2, J, plus V3 minus W3, K. You with me so far? Now, if you wanted to take the magnitude of that vector, how do you take the magnitude of a vector? You use the Pythagorean theorem. You square each of the coefficients of the components, add them together, and take the square root. Great. Can we do all the things on the right? Oh, the right-hand side is just a lot of easier pieces. Do you know how to take the magnitude of this? Magnitude, oh yeah, sure. There's a bunch of, not that much, a medium amount of algebra you need to do. And if you do out the algebra carefully, algebra, yay, you end up with this. V1 W1 plus V2 W2 plus V3 W3 is equal to the magnitude of V, the magnitude of W, cosine theta. If you use all of what you know, it doesn't take that long. If you use all of what you know, you get this. There are certain moments in your math career where you're presented with things that are super, super, super useful, but it's not immediately apparent why. Here's why this is super useful. One of the reasons. First of all, if I gave you two vectors, how hard is it to find this quantity right here? Not particularly. It's literally adding, multiplying and add, multiply, add, right? Can you take the magnitude of a single three-dimensional vector pretty easily? Absolutely. Theta is the same theta up here, right? What does this formula effectively allow you to find really easily? The angle. Can you isolate theta pretty easily given that you're BC calculus students? Yeah. Divide both sides by this and take the inverse cosine. This formula, first and foremost, allows you to find the angle formed between two vectors relatively quickly. You with me so far? The second thing is that a certain angle measure, which proves to be super useful, gives you a really, really, really powerful result. If these are two non-zero vectors, what does that mean about the magnitudes of each of the vectors? They are not what? They're not zero. They're greater than zero. They're greater than zero. Exactly. They're not zero, right? What's the only way for this thing right here to be equal to zero, this side? Cosine theta is the only thing that can be equal to zero. If that's not zero, that's not zero. So what does that have to be? Zero. So the only way for this to be zero would be cosine theta is zero. What values of theta make cosine zero? What's the smallest one? No. Pi over 2.
Then 3 pi over
3 pi over 2, then rotate it. It's pi over 2 plus pi n, right? You with me so far? How many degrees is pi over 2? 90 degrees. So if this is 0, it means that you plugged in something that makes it 90 degrees, right? Translation. If this comes out to 0, what do you know about the two vectors?
Oh, they're
What's it called? Perpendicular. Is this relatively easy to do? Is this relatively easy to do? Yeah, it is. This is super relatively easy to do, right? If this comes out to 0, it means that that value has to be 90 or 270. Either case, you know that the two vectors have to be what? Perpendicular. So this gives you an easy way to find out, first and foremost, what the angle measure is between two vectors, but really quickly, what can you figure out? If the two vectors are perpendicular or not. Because if it comes out to anything else, the vectors are not perpendicular. And U and V can represent what? Any two vectors in 3 space. So we were totally stuck to the board in 2 dimensions, right? Now we can have this thing floating in space where if we tried to do this kind of question before, we would have had to do like rotational stuff. Ooh, very cool. This thing right here, this is called the dot product. This is the dot product of the two vectors. There are two ways to determine the dot product of two vectors. This number, this is a scalar. This is a number right here on the left-hand side because this is a constant times a constant plus a constant times a constant. The dot product is always a scalar. This is the dot product. This is also the dot product. Sometimes you have the components, so you can do it this way. Sometimes you're given the magnitude and the angle, and what can you then find? The angle measure. What's really interesting about this, does the magnitude actually change the angle between two vectors? Not really. See, that's one thing I want you to like put a pin in your minds. How does that come into play? But the idea is, you have two different ways to find the dot product. And is the dot product going to be super, super helpful in moving forward in this class? Absolutely. Absolutely super, 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 super important.